For the first 30 seconds, Mars looks like a triumph. For the next 1,000 days, it's a slow, constant fight to stay alive. In this video, you're not just landing on Mars. You're living there, slamming into thin air at 6 kilometers a second, breathing manufactured atmosphere, watching your bones forget 1G, and trying to build a real base while radiation, dust, and distance quietly try to kill you. But before we continue, please subscribe to the channel if you enjoy the video. Let's continue. You don't really land on Mars, you crash in a controlled way, or you die. When your ship reaches the top of the Martian atmosphere, you're moving about 6 to 7 kilometers every second. At that speed, there is no turning around, no abort, no second attempt. Earth is about 225 million kilometers away, on average, so any help is at least 6 to 9 months behind you. From this point on, either the hardware and software work exactly the way they were designed, or your whole mission ends in the next few minutes. The Martian atmosphere is a bad compromise. It's less than 1% of Earth's sea level pressure. That means it's thick enough to heat your heat shield into a cloud of plasma, but too thin to slow you down the way Earth's air does. Outside the capsule, the shield is taking brutal heating. Inside, you're in a shaking metal shell, watching numbers, listening to call-outs, feeling the deceleration build. You're not heroically flying a ship. You're strapped into an automated system and trusting that years of testing on Earth did not miss something simple. The guidance computer tilts the capsule to control how much atmosphere you plow through. A few degrees more angle. You dig in and slow down harder. A few degrees less, you skip and travel farther. You're still moving faster than any rifle bullet, and all of this has to run on code that cannot crash or lag. At this point, the phrase "you made it" means one thing only. The aerodynamics, the materials, and the software are not failing in real time. If the air is this thin and this unreliable, how do you ever slow down enough to actually reach the surface in one piece? On Earth, parachutes are your main brakes. They grab thick air and turn speed into drag very efficiently. On Mars, air density is so low that parachutes are almost useless unless you deploy them while you're still supersonic. So that's exactly what you do. While you're still going faster than the speed of sound in a carbon dioxide atmosphere, the system fires a mortar, the parachute shoots out, the lines snap tight. This doesn't feel gentle. The jolt is sharp. Your harness digs into your shoulders, your body wants to keep going forward while the ship slows down hard. That parachute fabric was pushed in wind tunnels, on high-speed test flights, and in simulations because there is zero room for failure. If the canopy rips here, or the lines tangle, you do not have enough atmosphere or altitude to try another solution. You just keep falling. Even with the parachute fully open, you are still dropping too fast. The atmosphere is too thin to slow you down to safe landing speed. So now you're in a weird middle state, slowed down compared to orbital speed, but still heading toward the ground at hundreds of meters per second. The parachute alone can't save you, so what takes you from still a fatal fall to standing on the surface in the last stretch? Somewhere a few kilometers above the ground, the lander cuts the parachute. For a moment you're just falling. Then the retro rockets fire. Engines on the lander push hot exhaust downward, fighting Mars's gravity. The guidance system is reading radar altimeters, checking velocity, adjusting thrust many times every second. A little too much thrust, you burn extra fuel and risk running dry before touchdown. A little too little, you hit harder than the structure can handle. As the engines fire, they blast the surface and throw up clouds of fine dust in all directions. Martian dust is made of very small, sharp grains. It sticks to everything, and it's abrasive. It sands your landing legs, covers cameras, and tries to get into every joint and seal. Engineers knew this. They designed hardware assuming that this first landing is also a controlled sandblasting event. Right now, though, you only care that your sensors are still reading the ground correctly through this mess, and that the engines don't ingest too much dust and choke. The final phase is brutal and short. The computer has to bring your velocity towards zero right as you reach the surface. A few percent error, in thrust, or a few seconds of wrong timing are the difference between a working lander and a wreck. When you finally feel the impact, it's a hard, sharp thump as the legs take the load. The engines shut down. Dust continues to move around you. For the first time, you are not in free fall or in deep space. You are sitting on Mars. You might think the next step is to open a hatch and walk outside for a historic first step. That's not how it works. Your real first step on Mars is standing up inside a metal can. After months in microgravity, your body has been floating in 0G. Now you're in 0.38G. That's more than the cruise, but much less than Earth. Your inner ear is confused. Your blood distribution has to adjust. Your muscles are weaker. You unstrap carefully, push yourself up, and feel weight in a strange, reduced way. You don't stride, you test every movement. And you are still breathing only because your habitat is doing its job. The air in here is not natural. It's a manufactured product. Engineers aimed for something like Earth's mix, around 78% nitrogen and 21% oxygen, but at a total pressure lower than Earth's, maybe 70 to 80 kilopascals instead of 101. Lower pressure means less structural stress on the walls and windows. Sensors are monitoring CO2 in parts per million, humidity, trace contaminants, and pressure changes down to tiny fractions. If anything drifts out of range, alarms will trigger and someone has to fix it. Outside, the air is almost a vacuum compared to what you're used to. Inside, it's a controlled bubble, shaped completely by machines and power systems. You grew up taking atmosphere for granted. From now on, every breath depends on pumps, filters, valves, tanks, and software. So do you now relax, say some dramatic words, and enjoy being the first person on Mars? Not yet. Before any speeches, you walk through the Sol Zero checklist with your crew. You check external pressure, around 600 pascals, which is about what you'd see 35 kilometers above Earth's surface. You check external temperature, maybe minus 60 degrees Celsius on average. But you read the exact value at your site and look at the expected day-night swing, which can be more than 70 degrees. You verify oxygen levels in the habitat, CO2 levels, leak rates, fan status, and power margins. Then you look at radiation. Instruments tell you how much cosmic radiation is hitting you on the surface. Roughly 0.6 to 0.7 millisieverts per day, several times what people get on the space station. You log that. You know that every sol you stay here, that dose adds up. It doesn't hurt now. It just changes your future odds of cancer and other problems. You don't celebrate when the numbers look dramatic. You celebrate when they look boring and stable. Only then do you let it really sink in. You are alive. On Mars, inside a machine that has to keep working every single day for the next 1,000 days. And if just surviving the landing and the first sol is this demanding, what is going to happen to your own body over those 1,000 days, when your bones, muscles, blood and brain live year after year in only 0.38 grams, under constant radiation, and far from any real help? Your body is already in trouble before you ever see Mars out the window. The damage starts during the trip. In microgravity, your skeleton and muscles decide they are not needed. Without heavy exercise, astronauts lose around 1 to 2% of their bone mineral density every month, and muscle mass can drop by 20% or more. Your spine stretches, your posture changes, your back can ache because the discs between your vertebrae swell. Your heart also rewires its job. In 0G, it doesn't have to pump blood uphill to your brain, so it remodels, it can get a little smaller, and your blood volume can drop. By the time you hit Mars, you are not the person who left Earth. You are slightly taller, weaker, with bones that have already started to thin, and a cardiovascular system tuned for floating, not standing. Then instantly the environment flips. You go from 0G in cruise to 0.38G on the surface. It's heavier than you've felt in months, but still way lighter than home. Your body has to pick a new normal, and it has no evolutionary script for this. So what actually happens in those first minutes when you try to stand up in Martian gravity? When you push yourself out of the seat, 0.38G feels strange. Your inner ear, the part of you that senses balance and motion, finally has a gravity vector again, but it's weaker than your brain expects. Your muscles fire with the memory of Earth, and you overshoot or move in stiff, careful steps. Your legs, already deconditioned from months in 0G, struggle to figure out how much force to produce. Simple actions like walking across the cabin feel awkward and slow. If you do a small hop, you rise higher than your instincts predict, and you land slower. It's not heroic slow motion, it's just slightly off. enough that every movement feels like it needs a mental correction. For years, scientists have argued whether 0.38 G is enough to keep human bones and muscles healthy if you live in it long term. On the Moon, with about 0.16 G, the guess is that it's too low. On Earth, 1 G is obviously enough. Mars sits right in the unknown zone. Your first 1,000 days on the surface are not just a mission, they are a live experiment in what partial gravity does to a human body. If your bones and muscles are already weakened, how do you stop them from just getting worse every single day you stay on Mars? The answer is simple and harsh. You turn exercise into a non-negotiable part of survival. You do not get to skip leg day. On the space station, astronauts already spend around 2 hours a day on exercise, using resistance machines, treadmills with harnesses to pull them down, and cycle ergometers. On Mars, you keep that habit, maybe with even more focus. Your schedule builds in long blocks of training, whether you feel like it or not. You use resistance machines that simulate heavy weights to load your hips and spine. You run on treadmills while a harness pulls you down, so your feet actually impact the belt. You cycle to push your cardiovascular system. If your mission has advanced hardware, you might even have a short-arm centrifuge, a spinning device that gives parts of your body temporary, higher effective gravity, trying to trick your bones and blood vessels into thinking they are back on Earth for a while. This is why people call it an exercise prison. It doesn't matter how much work you did outside, how tired you are, how busy the schedule is, the long-term risk from bone loss and muscle atrophy does not care. Without this constant loading, your skeleton keeps dumping calcium, your muscles keep shrinking, and your risk of fractures and weakness climbs. Even with exercise, you might only slow the damage, not stop it. Scientists are betting that a mix of 0.38 grams plus heavy daily workouts is enough. If they're wrong, you will feel that mistake in your own body. And it's not just bone and muscle. Your blood and the way it moves around your body also has to relearn gravity. What does that feel like when you actually stand up and start working? In microgravity, fluids drift toward your head. Faces puff up, legs thin out, blood volume changes. Your body treated that as the new baseline. On Mars, gravity pulls fluids back down again, but your system is not ready. Stand up too quickly and you can get lightheaded. In the worst case, you hit orthostatic intolerance, where your heart and blood vessels don't react fast enough, blood pressure drops and you can faint. A blackout on Earth is embarrassing. A blackout on Mars, inside a suit or in an airlock, can be lethal. So you and your medical team watch this closely. You check blood pressure, heart rate, and how you feel when you stand, when you squat, when you carry loads. Plasma volume may have to be boosted with extra fluids and salts. Every EVA you do, every time you gear up, step into a rover, climb a ladder, you're testing whether your circulation has truly adapted to 0.38 G, or if it's still stuck in microgravity mode. If your body is struggling with gravity and blood flow. What does all of this do to your brain, your sleep, and your sense of time? When even the length of a day is wrong. A Martian soul is 24 hours and 39 minutes. That extra 39 minutes sounds small, but it punches your internal clock over and over. Human circadian rhythms on Earth naturally run a bit longer than 24 hours, but not by much. On Mars, you're forced to live on a 24-39 schedule, every day for around 1,000 sols. If you don't manage that carefully, your sleep phase slides, your hormones drift out of sync, and your performance drops. To stay sharp, you use light and timing as tools. Bright light, especially blue-rich light, at certain times of your morning, pushes your internal clock earlier. Reducing light exposure before sleep helps you wind down. Some days you may use melatonin to nudge your brain towards sleep at the right hour. Your schedule for work, meals, EVAs, and exercise is anchored to this slightly stretched soul, and everyone on the base has to follow it tightly, or the crew drifts out of sync with each other. When your sleep quality drops, your reaction times slow, your memory gets worse, and your mood can crash. On Mars, that's not just uncomfortable, it's unsafe. A tired person misreading a number on a life support panel, or fumbling a procedure in an airlock, can start a chain of failures nobody can stop in time. That's why, out here, light management, sleep discipline, and psychological support sit in the same critical category as oxygen and water. So now your body is weaker than when you left. Your bones are under new stress, your heart and blood are relearning gravity, and your brain is being forced onto a 24/39 clock. All of that is happening while you live inside a closed metal shell on a world with almost no air, where every system can kill you if it fails. If just staying in one piece is this hard, how do you keep breathing, drinking, and dealing with waste for 1,000 days? On a planet where you cannot step outside and just grab anything you need. On Mars, air is not background. It's a machine that can break. Your habitat is a closed loop, or you die. There is no huge sky to dilute your CO2, no wind to carry away leaks, no outside source to fix bad chemistry. Every breath you exhale adds carbon dioxide to a small, sealed volume. If nothing removes it, CO2 climbs from harmless levels into ranges that cause headaches, confusion, and then unconsciousness. So your life rides on hardware with one job: pull CO2 out and keep oxygen high enough to live. Inside the walls, air flows through scrubbers. Some systems use solid amine beads that grab CO2 when they're cool, then release it when they're heated, so the gas can be vented or stored. Older systems use lithium hydroxide cartridges that lock away CO2, but those are single-use, so long missions avoid them except as backups. Advanced regenerative systems cycle their absorbent material over and over. Oxygen comes from high-pressure tanks you brought from Earth, from splitting water by electrolysis, and later from Martian resources you tap on site. Every kilogram of gas or water you don't have to launch from Earth saves a huge amount of money and rocket fuel. So clever chemistry is not a side project, it's core life support. If the air outside is mostly carbon dioxide, can you actually turn that into something you can breathe? Or is it just useless background? The thin Martian atmosphere is about 95% CO2. That sounds like a problem, but it's also an opportunity. Tech, like the MOXIE experiment on the Perseverance rover, has already shown that you can take in Martian CO2, run it through a hot solid oxide electrolysis cell, and split each molecule. Oxygen atoms are pulled out to make pure O2. Carbon atoms pair up as carbon monoxide. MOXIE only makes grams of oxygen per hour, but for a base, you scale that up. Now you have an oxygen factory that runs as long as you feed it CO2 and electricity. Over 1,000 days, you don't think of air as fresh or stale. You think of it as numbers on a screen. Oxygen partial pressure, CO2 partial pressure, total pressure, flow rates. Power draw from your ISRU units, the in-situ resource utilization machines that pull raw inputs from the local environment. You schedule high-power O2 production runs when your solar panels and reactors have margin. You watch storage tanks fill and empty. A simple leak or compressor fault can show up as a slow drift in those graphs, long before anyone feels short of breath. Air is one side of it, the other is water. How do you drink, wash, and grow anything in a place where liquid water doesn't just sit on the ground? On Mars, you treat water like treasure. The average person needs about 3 to 5 litres of clean water every day, just for drinking and food. Add hygiene and any plant growth, and the demand jumps. At the start, almost all of it is recycled. You pee into a system that distills and filters it, pulling out more than 90% of the water content. Humidity in the cabin air condenses on cold surfaces and gets captured. Grey water from sinks and showers goes through filters, membrane, tar, and maybe advanced oxidation to strip out soaps, organics, and microbes. Nothing goes away. Every drop is either recovered or it's a permanent loss you feel in your tanks. Over time, you don't want to rely only on recycling, so you turn to the planet itself. Radar scans from orbit show buried ice in many regions, sometimes in huge slabs close to the surface. You send out drills and excavators, dig into the regolith and haul back icy dirt. That mix then goes through heaters. Ice turns to water vapour, which is condensed into liquid. But it's not ready yet. Martian soil holds perchlorates and salts. Those can be toxic. So you push the water through filters, ion exchange, or chemical treatment until it meets strict purity standards. Mining, chemistry, and survival all blend into one job. If you're squeezing water from your own waste and from dirty ice under the ground, What do you do with all the solid waste that keeps piling up? Is it just trash or is it something you can use? On Mars, waste is a resource with bad PR. Every bit of organic material leaving your body and every scrap from your food and plants contains carbon, nitrogen, and other elements that your farm systems need. Instead of dumping it, you route it into controlled bioreactors. There, carefully chosen microbes break it down. Solids turn into simpler compounds, releasing nutrients that can feed hydroponic or aeroponic setups. Liquids are again stripped of dangerous contaminants, then reused. Food scraps, packaging that can be chemically processed, dead plant matter from your crops, all of it gets shredded, sorted, and either composted or sent into higher temperature reactors that crack long molecules into simpler ones. On Earth, you flush a toilet and the story ends for you. On Mars, flushing is only step one. Somewhere downstream, some part of that output ends up in a tank feeding your tomato plants, or in a line that eventually comes back to your drinking water. It's not pretty, but the physics is simple. You are in a closed loop, and ignoring that fact just means running out of supplies sooner. If everything is so tightly recycled, what happens when something in the system drifts a little off-spec? Just enough that nobody notices right away? This is where life support feels like living next to a constant, quiet alarm. Sensors sample the air every few seconds. They watch oxygen, CO2, water vapour, and also trace gases like ammonia, carbon monoxide, and volatile organics from plastics and lubricants. Other sensors track water chemistry, pressure in tanks, flow rates through lines, filter back pressure. Software flags trends. A fan running slightly slow, a filter starting to clog, a very small leak in a valve. All of these can show up first as tiny, slow changes on graphs. Over 1,000 days, you know for sure that things will fail. Pumps wear out, valves stick, seals age under radiation and dust. The real question is how many things fail, in what order, and whether you notice early enough to break the chain. That's why everyone on the crew becomes at least a part-time life support engineer. You learn the normal shape of the data. You know what the CO2 curve should look like when everyone sleeps, or when the greenhouse lights kick on. When it looks wrong, you dig into it before it becomes an emergency. If you miss it, if a slow leak goes unnoticed, or a scrubber quietly loses capacity, physics doesn't negotiate. Gas concentrations drift out of safe ranges, and by the time anyone feels dizzy or short of breath, you're already behind the curve. On Earth, you can open a window. On Mars, there is no safe outside. The only air you will ever breathe comes from machines that can break, in ways you haven't even seen yet. So now your air, your water, and even your waste are all locked into fragile loops of hardware and chemistry. You've turned the planet's thin CO2 into oxygen, its buried ice into drinking water, and your own waste into plant food. But there is one thing you cannot filter out or recycle away, something that cuts through steel, regolith and flesh, slowly and constantly, every single soul. What does it really mean to live for 1,000 days under Mars radiation, with almost no magnetic field, in a place where the sky itself is a source of damage? On Mars, radiation is not an occasional threat. It's the background of your entire life. The planet has almost no global magnetic field, and only a thin atmosphere. So high-energy particles from the galaxy hit the surface much more directly than on Earth. Instruments like Curiosity's rate have measured around 0.67 millisieverts per day on the ground. Stretch that over 1,000 days, and you're looking at hundreds of millisieverts, getting close to, or even past, some agencies' lifetime limits for astronauts. This is not the movie version of radiation. No glowing green goo. No instant superpowers. You don't feel anything. You don't see anything. But on the molecular level, charged particles are punching through your body, ionizing atoms, breaking DNA strands, and causing damage that your cells then have to repair. Sometimes they fix it correctly, sometimes they don't. Misrepaired DNA can turn into cancer years later. Radiation can also hit bone marrow, lowering blood cell production, and can slowly affect brain tissue and blood vessels. Every second you spend on Mars adds a small piece to a dose you can never erase. Because of that, you track radiation the way you track air and water. You wear a dosimeter on your body. Your suit has another. Your bunk has one nearby. The base has fixed sensors that log the environment hour by hour. You don't just care about the daily average. You care about spikes, about how much you get on EVAs, about how much shielding different parts of the habitat really give you. Your medical file fills up with radiation exposure charts right next to your blood tests. Most days, that exposure is a slow drip. But the sun can change the game in a single outburst. What happens when the star you depend on suddenly turns hostile? Solar flares and coronal mass ejections can launch huge clouds of energetic particles into space. On Earth, our magnetic field and thick atmosphere catch almost all of that, so people on the ground barely notice, apart from maybe a pretty aurora. On Mars, there is no such shield. If one of these events hits the planet directly, radiation levels can spike fast, in minutes to hours, and stay high for many hours or days. If you're on the surface during one of these solar particle events, without good shielding, the dose can go from slowly adding to cancer risk to acutely dangerous in one hit. That's why your base has storm shelter zones built in from day one. These are spaces buried under thick regolith, or wrapped in water tanks and other hydrogen-rich materials that are good at absorbing radiation. They might be narrow, cramped, and not pleasant, but they're where you go when the sun gets angry. Radiation alerts are treated like fire alarms. When a warning comes from solar observatories and spacecraft watching the sun, you don't debate it. You cancel or abort EVAs, you get rovers and suits back to safe positions, you move people into shielded areas, you log who went where and when. All of this has to be drilled, because when the real event hits, there's no time to argue over procedures. On Mars, go to the shelter now is as serious as don't open that airlock. You can't put a magnetic field around Mars, so you use what you do have, the ground. How do you turn a dusty, dead landscape into a shield between you and space? The regolith under your boots, the loose rock and dust is your best passive defense against cosmic rays and solar particles. A couple of meters of it, packed over a habitat, can cut your annual dose significantly. It's not perfect. Some high-energy particles punch through anything, but it helps. That means part of your first 1,000 days is not heroic exploration. It's heavy construction. You use bulldozers, robotic haulers, and maybe 3D printed structures to pile regolith over and around your living modules. You build berms and mounds. You partially bury modules in shallow trenches. You might even design new habitats that are meant from the start to be covered with several meters of local soil. From orbit, your base slowly changes from a cluster of exposed metallic shapes into a series of low, dusty lumps blended into the terrain. Sleeping under a few meters of regolith is not comfortable in a psychological sense. There is no clear view of the sky, no easy sense of outside. But your dosimeter reads lower in those spaces, and over years that difference can mean fewer damaged cells, fewer mutations, less stress on your body. In a direct way, you are hiding under what's left of Mars' lost atmosphere, compacted into rock and dust. Even with all this shielding, you're doing something no human has ever done, living for years in a place with almost no magnetic protection. What does that do to the rest of your biology? Beyond cancer risk? The honest answer is, we don't fully know. You are the experiment. Your blood chemistry is monitored over and over, looking for changes in immune function, inflammation markers, and signs that bone marrow is under stress. Doctors track how often you get sick, how well you recover from minor infections or injuries, whether your wound healing changes over time. They are watching for subtle shifts that might link to chronic radiation exposure plus partial gravity. Your nervous system and brain are also in the spotlight. There are concerns that long-term exposure to cosmic rays can affect cognitive performance, memory, and mood. So you regularly run through reaction time tests, problem-solving exercises, and psychological evaluations. You fill out questionnaires about sleep quality, anxiety, and concentration. This is not just for your personal health. It's data to answer a big question. How does a human brain cope when the environment is quietly damaging it, day after day? Dosimeters sit everywhere. On you, in your suit, on the walls, in equipment racks, even buried in the regolith around the base. Tiny detectors might go out on rovers, mapping radiation levels in different terrains, near cliffs, inside small caves or lava tubes. You're not just living under this invisible storm, you're charting it. And all of this is happening in parallel with everything else. Gravity stress, life support maintenance, isolation, and the daily work of running an outpost. Radiation does not pause while you sleep or while you fix a pump. It's always there in the background, slowly adding up. If even the sky is attacking you like this, what does that do to your sense of time and routine? When your day is the wrong length, your seasons are stretched, and every message from home arrives late. On Mars, even the length of a day fights you. One sol is 24 hours and 39 minutes. That extra 39 minutes looks harmless on paper, but it wrecks normal schedules. If you lock your operations to local solar time, sunrise and sunset, your internal base clock drifts about 40 minutes later every Earth day. After a month, your morning meeting happens in the middle of the night, relative to people on Earth. After a year, your day-night cycle has marched through every possible phase compared to home. This hits everything. Sleep, work, maintenance, EVAs, communications, windows with Earth, all of it. If you stick with pure Mars time, your body is forced to live on 24/39. While Earth support teams are stuck at tasks 2400. That means you either let your schedule drift relative to mission control, or you force someone to live in permanent jet lag. If instead you lock your internal schedule to Earth-like 24-hour days, then your noon inside the base slowly slides away from actual local noon outside. That can make EVA timing and thermal planning harder. So you end up making a trade. Some crews choose full Mars time, accept the slow spin away from Earth clocks, and let the support teams back home adapt with rotating shifts. Others choose a hybrid, maybe stick to Earth-like days most of the time, then adjust a bit to keep critical EV, as lined up with good sunlight and temperatures. No option is clean. Over 1,000 days, your body, your work habits, and your communication patterns are all stretched by that extra 39 minutes, over and over. The day is wrong, and the year is wrong too. What happens when the seasons themselves run on a different clock? Mars takes about 687 Earth days to go once around the Sun, almost 2 Earth years. Its axis is tilted by about the same amount as Earth's, so you still get spring, summer, fall, and winter. But each one is stretched out and distorted by the planet's more oval orbit. A Martian winter is not a quick 3-month phase. It can last hundreds of sols. And as Mars moves farther from the Sun in its orbit, the total sunlight hitting the planet drops, which amplifies the seasonal energy drop. This shows up directly in your power budget. Solar panels that already get only about 43% of Earth's sunlight now see even less during parts of the Martian year. At the same time, dust storms are more common in certain seasons, especially when Mars is closer to the Sun and the atmosphere is energized enough to kick off global-scale events. Your first 1,000 days might just cover 1.5 Martian years, so you barely get a full cycle to learn how summer and winter really feel here. In practice, that means you don't just plan for days, you plan for long, stretched seasons. You stock more energy storage and backup power to ride through dark periods. You schedule big construction or exploration pushes when light is good and temperatures are less extreme. You expect long, dragging winters where outside work nearly stops and cabin time increases with all the psychological load that brings. The phrase "winter is coming" stops being a joke and becomes a multi-hundred sol operational problem. If your days and seasons are all running on alien timing, what does that do to your head when your brain is still wired for Earth? Your internal clock, your circadian rhythm, evolved for a roughly 24-hour cycle. Lab studies on Earth show that humans can stretch a little beyond 24 hours, but being forced to live on a 24/39 sol for years is something we've never tested in real conditions. On Mars, you are the test. Crew planners try different strategies. Some missions try pure Mars time, everything synced to the local sol. Others try staying close to 24-hour days, using timed lighting and strict routines to hold the line. Some experiment with more complex hybrids like blocks of Mars time, followed by reset periods. None of this fully removes the strain. Over months, even a small mismatch between your internal clock and your imposed schedule leads to sleep problems, trouble falling asleep, trouble staying asleep, or waking up at the wrong time. That in turn feeds mood swings, irritability, and dips in cognitive performance. Jet lag is the wrong word, because there is no arrival where you finally sync. It's more like living permanently on a slightly broken clock, where your body is always trying to shift one way while the mission schedule pushes another. You use tools, bright light therapy at controlled times, dark periods before sleep, strict rules on when people can nap, and possibly medications like melatonin. You monitor not just how long people sleep, but how well they sleep, using wearables and questionnaires. When someone's performance tests start to slip, the first question is often, how many good sleep cycles have you had this week? Because here, a tired brain isn't just inconvenient, it's a direct safety risk for airlocks, vehicles, power systems, and life support. On top of that, you are cut off from real-time human contact with Earth. How does that delay change the way you think about time, help, and even relationships? Light takes between about 4 and 24 minutes to travel one way between Earth and Mars, depending on where the planets are in their orbits. That means a round-trip message takes between roughly 8 and almost 50 minutes. Over your entire 1,000-day stay, you will never have a live conversation with anyone on Earth. No phone calls, no real-time video chats, no instant troubleshooting. Everything is messages, like very slow email or voice notes. You record a question, send it, and then you wait. By the time their answer arrives, your local situation may have already changed. That forces you to shift how you see authority and support. Mission control can give guidance, but they cannot micromanage your minute-to-minute life. In an emergency, they can't talk you through each step fast enough. The crew on Mars has to become much more autonomous, making decisions on the spot, and then later syncing up with Earth about what they did. Socially, this delay rewires your sense of connection. You can still get messages from family and friends, with video and text, but the back and forth is slow and out of phase. By the time you react to their news, they've already moved on. Holidays, birthdays, and events on Earth reach you late, and your replies land even later. You stop expecting instant answers. You stop reaching for your communicator the way you would reach for a phone on Earth. Over time, the culture inside the Mars base starts to drift. Inside, everyone lives on the same strange soul length, shares the same local problems, and reacts to the same immediate conditions: dust storms, power issues, equipment quirks. People on Earth live by a different clock, different seasons, and different pressures. That split deepens the longer you stay. In practice, you start to feel like you live in a different time, not just a different place. So now your day is too long, your year is stretched, your sleep is under constant pressure. And every message from home comes with a built-in delay. Your mind has to rebuild its idea of normal time from scratch, while still staying sharp enough to handle radiation, life support, and harsh weather. If that's the mental background, what happens when you face something much more basic and relentless? The need to eat every single day. On a planet where food is insanely heavy to ship, agriculture is experimental, and even your trash has to become fertilizer just to keep you going. Food is one of the most boring and most brutal problems you face on Mars. It's not about taste first, it's about mass. A human needs roughly 0.8 to 1 kilogram of dry food every day, plus water in that food and all the packaging. For even a small crew, say 6 people over 1,000 days, that's on the order of tens of tons of stuff. Every extra ton forces a bigger rocket, more fuel, more cost, and more risk. You simply cannot bring endless fresh food in boxes like a long camping trip. So the first months on Mars, your menu looks like it came out of a spreadsheet, not a cookbook. You eat dense, shelf-stable, freeze-dried meals, powders you rehydrate, vacuum-sealed pouches you warm up, bars that are balanced for calories, protein, fat, and micronutrients, not happiness. Everything is designed to last for years without spoiling, survive launch and landing, and be as compact as possible. You get enough calories, enough vitamins, enough protein, but not much joy. You can feel that in the crew. Small complaints about texture, about the same flavours looping over and over. But you all know why it's like this. Shipping food to another planet is a mass problem, not a taste problem. If shipping everything is that bad, how do you break that dependence on Earth and stop your stomach from being chained to a launch manifest? You turn your base into a small farm, whether you like gardening or not. To get real freedom from resupply, you need plants. You set up hydroponic racks, where roots grow in nutrient solutions instead of dirt. Or aeroponic systems, where roots hang in air and get hit with nutrient mist. LEDs provide light at carefully chosen wavelengths, usually heavy in red and blue, tuned for photosynthesis efficiency. You don't care about what looks pretty, you care about what grows fast and gives you the most calories and vitamins per watt and per litre of water. Early on, you grow things like leafy greens, lettuce, spinach, kale, herbs. They grow quickly, don't need much space, and give you fresh crunch and flavour that your freeze-dried meals can't match. As the systems stabilise, you push further, into dwarf wheat, potatoes, maybe beans or peas. On the space station, people have grown small amounts of lettuce. On Mars, you're trying to scale that up until it actually contributes a measurable chunk of your daily calories, not just a garnish. Photosynthesis stops being just biology, it's infrastructure. CO2 from your breath and from your life support. Exhaust is piped into the grow area. Plants absorb that CO2, use light energy to build sugars and plant tissue, and release oxygen back into the habitat system. Water cycles through tanks, filters, and root zones. Every kilogram of edible biomass that comes out of that loop is one less kilogram that had to be launched out of Earth's gravity well. It's a quiet but very real act of resistance against the cost of getting here. But you're on Mars, not Earth. There is no real soil. So what are your plants actually growing in? If the ground outside is toxic dust, Martian regolith is not friendly topsoil. It's a mix of basaltic dust, crushed rock, oxidizing chemicals like perchlorates, and various salts and metals. Perchlorates are especially nasty. They're reactive and toxic at the levels we expect in some Martian dirt. If you just shove a plant into raw regolith, you will probably kill it, and you may contaminate your water systems with chemicals you don't want near your food or your body. So instead, your Martian soil is a piece of engineering. First, you take regolith and sieve it, remove larger rocks, break up clumps and control the grain size. Then you wash it, or chemically treat it, to remove or neutralize perchlorates and some other reactive compounds. Now you blend it with composted organic matter from your waste streams, processed to kill pathogens, and maybe with inert support, media like clay pellets or fibres, to control drainage and aeration. What you end up with looks like soil, dark and crumbly, but chemically it's something you built, not something that just existed. You constantly test it. You measure pH, nutrients, salt levels, and how well it holds water. You adjust the nutrient solution you feed through your hydroponic systems to fill in what the substrate lacks. The goal is not to make pure Martian dirt farming happen. The goal is to use as much local material as you can, while still giving your plants a controlled, safe environment. In simple terms, you're forcing geology to behave like agriculture. Under all of this, there's another layer you cannot see, but absolutely depend on: the microbes that make your closed ecosystem stable. How do you keep that invisible world from turning against you? On Earth, your gut microbiome, the bacteria in soil, and the microbes in water systems live in an open, huge environment with constant inputs and outputs. On Mars, everything is sealed and small. Your gut microbes change with stress, diet, and radiation. The bacteria in your compost reactors break down waste, releasing nutrients. Microbes in your water filters form films that can help or hurt. The whole microbial world inside the base is a delicate, artificial ecosystem. If one aggressive strain takes over a filter, it can clog lines or produce harmful byproducts. If your compost bioreactors shift to the wrong balance of species, they might produce too much gas, or not break down waste efficiently, or leak pathogens. Food safety is also under pressure. You absolutely cannot afford a major outbreak of food poisoning in a tiny, isolated crew. So you test constantly. You take samples from water, air, surfaces, and grow beds. You run them through microscopes, genetic assays, and chemical sensors. You also watch your own bodies. Changes in digestion, sudden increases in stomach problems, unexplained rashes or infections, all can be early signs that your controlled microbial environment is drifting. Sometimes the right response is simple cleaning and filter replacement. Sometimes you need to change temperatures, oxygen levels, or nutrient inputs in a bioreactor to push the microbe balance back into a healthy zone. Your food system is not just about calories and plant growth. It's about keeping an invisible living network stable in a place that does not naturally support it. At some point, if things go well, all of this work pays off in one quiet but huge moment. What does that look like when Mars finally feeds you more than Earth does? One day, months or years in, You sit down to a meal where most of the calories did not come from Earth. The main part of the dish is potatoes or grains, grown in your habitat, using water melted from local ice, in a substrate built from regolith and composted crew waste. The vegetables on the side, the herbs, maybe even some plant-based protein, all came from your own controlled farm. The only parts still mostly from Earth are trace ingredients, specific nutrients, or long-life items that are hard to produce locally. On the surface, it's just food on a plate. But the meaning is bigger. At that moment, Mars stops being just a hostile campsite that you keep alive with imported supplies. It becomes a place that can, in principle, sustain you using its own materials, as long as your systems work. You've closed a large part of the loop. You're not fully independent yet, far from it. But you've crossed a psychological and practical line. You also know how fragile it is. A failed pump in the greenhouse, a power drop during a storm, a disease that hits one of your main crops. Any of that can slam your food production and push you back toward rationing emergency stores. You're always one or two major failures away from feeling the weight of that mass problem again. And outside the greenhouse walls, there is another constant problem building up. Something that doesn't care about your plants, your lungs, or your mood. It just coats and grinds and clogs until your machines start to choke. What happens when the fine dust, the thin air, and the strange weather of Mars starts attacking everything you own, from solar panels to suit joints, every single soul? Most people think Mars storms will rip your base apart. That part is wrong. The planet can absolutely throw serious wind at you, speeds over 30 meters per second, the kind of numbers we call hurricane class on Earth. But the air is less than 1% of Earth's sea level density, so the actual force on structures is much smaller. Those winds are not going to flip your rover or tear your habitat off its foundations. Structurally, you can design around the loads. The real threat is what the wind carries and what it does to your power. Martian dust is made of micron-scale grains, so small you could fit dozens across the width of a human hair. They charge up electrically as they move, so they cling to surfaces, especially anything made of glass, plastic, or metal. A light coat on your solar panels can cut power by 30%. A heavy coat during a long storm can push that to 50, 70, even 90%. That's not a minor loss, that's the difference between running heaters and pumps normally, or going into emergency mode to keep batteries from dropping below safe levels. Wind picks up this dust and keeps it suspended for long periods. That means you get not just a dirty panel, but a whole sky that's hazy and dim. It's not a dramatic wall of sand slamming your base. It's a long, choking reduction in light and visibility that just keeps dragging on. You don't fear getting blown away. You fear getting powered down. Local storms are bad enough. But what happens when those local storms connect and wrap around the planet? Every few Martian years, a set of storms can merge into a global or near-global event. In 2018, one of these ended the Opportunity rover's mission. The rover didn't get smashed by wind, it simply lost the sun. Dust thickened the atmosphere so much that sunlight at the surface dropped to a fraction of normal. The rover's solar panels could no longer generate enough power to keep the systems warm and alive, and it slipped into silence. In your first 1,000 days, the odds are not low that you'll face at least one serious regional storm, maybe even a planet encircling one. You see it coming first in data from orbiters and ground sensors, dust opacity numbers, climbing images showing a fuzzier horizon. Outside, the light shifts to a flat, muted orange or brown. Shadows fade. It feels like permanent late evening, even at midday. Your response is procedural. The base moves into storm mode. You postpone non-essential EVAs. You secure loose external gear. You shift as much power generation as possible to nuclear or stored energy, knowing solar output is about to crash. You start carefully rationing high-draw systems, maybe dimming lights in non-critical areas, reducing greenhouse lighting if your plants can tolerate short dips. Inside, you swap filters more often, because the dust that sneaks in through airlocks and tiny leaks loads them up quicker. You log power in and power out obsessively, because in a long storm you can't afford surprises. Once the storm hits full strength, almost all exterior work stops. Visibility drops, navigation cameras get foggy with dust, fine particles try to work into every moving part. You are effectively blind and half-deaf outside your walls. The planet has told you very clearly to sit still. That dust does not just block light, it physically goes after your hardware. How does that play out over months and years? Dust is one of the main ways Mars kills machines. It gets everywhere. Suit bearings, rover suspensions, wheel hubs, hatch seals, airlock hinges, ventilation intakes, radiators, connectors, you name it. Each grain is tiny, but they are hard and often sharp, made of basalt and sometimes glassy fragments. Every time you move a joint or a mechanism with dust inside, you're running a microscopic sandpaper over it. Over months, seals that looked solid on day one develop tiny scratches and wear marks. Viewports and camera lenses pick up fine haze as tiny impacts and rubbing events accumulate. Radiator fins trap dust, reducing their ability to dump heat. Air filters load up faster than their design models predicted, because this environment is worse than any test chamber on Earth. Dust also isn't chemically innocent. Perchlorates and other reactive substances ride along on those grains. They can help corrode metals, degrade polymers, and interfere with electrical contacts. That's why housekeeping becomes a survival task. You spend a lot of time vacuuming floors, wiping surfaces, brushing suits, blowing off equipment with air jets, and running external cleaning systems on panels and radiators. What would be janitor work on Earth is critical engineering work here. You also design equipment to fight back. Suit ports that keep dusty outer layers mostly outside the main habitat. Double-door airlocks with dedicated dust cleaning stages. Rovers with sacrificial covers on key joints. Solar panels with brushes, wipers, or even electrostatic systems that can shake off dust using electric fields. Every design review on Earth has a section that says, okay, now, how does Mars dust ruin this? And what are we doing about it? For all its problems, the Martian atmosphere is not useless. Is there any way to turn this thin, annoying gas and dust mix into something you can actually use? Even at less than 1% of Earth's sea level pressure, Mars air is thick enough for some tricks. When you send heavy cargo to Mars, you can use aerobraking, skimming through the upper atmosphere multiple times to slow down without burning huge amounts of fuel. Each pass through the air bleeds off some orbital energy. You combine that with heat shields and careful guidance, and you turn the thin atmosphere into a free break. Closer to the ground, you can use it for flight. Not the way you fly planes on Earth, but with specially designed aircraft. Think drone-style vehicles with very large rotor blades or wings, spinning or moving slowly through the thin air. NASA's Ingenuity helicopter has already shown this is possible, with short flights on Mars. Scale that up, and now you have flying scouts that can map terrain, inspect hazards, or check solar farm conditions without sending humans on long rover trips. Even wind, which is too weak to push heavy objects much, still has enough momentum to move dust. That's both a curse and a potential help. You may be able to design structures that channel natural winds over solar arrays, using them to help clear panels during certain seasons, at least partially. Or you may deploy tall, simple structures that catch dust first, sacrificing themselves so that key surfaces behind them get hit less. Over 1,000 days, you stop seeing the atmosphere as just a hostile, thin gas that brings dust and radiation. You start seeing it as a system with rules you can exploit. It's still unforgiving, but it's not pure enemy. It's another piece of the environment you can learn and bend bit by bit to your needs. And yet all of this, the storms, the dust, the thin air, are still outside. At some point you have to leave the relative safety of the habitat, seal yourself into a suit, and step directly into that environment to actually explore the planet. What happens when every walk outside, every drive in a rover, turns into a high-risk operation where your clothes are a one-person spaceship, and the ground under your boots is an ancient, possibly once wet world you're only just starting to read? Every time you step outside on Mars, you're not putting on a suit. You're getting into a small spaceship wrapped around your body. Outside pressure is roughly 600 pascals. Inside your suit, you need something like 30 to 50 kilo pascals to stay alive. That's around 50 to 80 times higher than the outside. All that pressure is pushing out through the suit walls all the time. A tear, a bad connector, a stuck valve, or a cracked visor is not a minor issue. It's minutes to unconsciousness. And if nobody fixes it fast, that's it. The suit has to provide pressure, oxygen, cooling, waste handling, communications, and protection from dust and radiation. It has to do all of that and still let you bend your arms and legs, grip tools, climb ladders, and get in and out of rovers. Every joint fights you because you're pushing against pressurized layers. Designers tuned mass and stiffness for 0.38 g, so the suit doesn't feel as heavy as it would on Earth, but it still wears you down. A long EVA is work just from moving the suit, even before you start lifting anything else. Before you go out, you and another crew member do detailed checks. Pressure integrity, oxygen flow, cooling loop, radio, battery level, telemetry. You confirm settings, sign off checklists, and only then cycle the airlock. When the outer door opens, there is no close enough safety margin. Either everything is working or you are betting your life on luck. With that level of risk just to walk a few meters, how do you explore anything beyond the immediate landing site without burning out your body and your time? That's where rovers become your second skeleton. On foot, in 0.38 g, in a stiff suit, you can cover maybe a couple of kilometers with a safety margin, then you have to turn back. With a pressurized rover, your operating radius jumps to tens of kilometers from the base. These vehicles are basically small mobile habitats on wheels. They have their own life support, oxygen storage, CO2 scrubbing, thermal control, radios and power, often a mix of batteries, solar panels, and maybe a small nuclear source for steady baseline energy. Inside a pressurized rover, you can take your helmet off, work in shirt sleeves, run instruments directly, and move more freely. You dock suits to the outside or carry them in an airlock compartment. The rover carries sample racks, drills, ground-penetrating radar, spectrometers, and whatever specialized gear your mission needs. Over 1,000 days, your EVA and rover logs start to look like dense maps showing every path taken, every outcrop visited, every drill site. You're not joyriding for views. Each trip is targeted, based on orbital data, previous measurements, and a long list of scientific questions about how this region formed. You drive across ancient floodplains, the edges of old crater lakes and lava fields. But to make that mean anything, you have to read the rocks directly. What does that look like in practice when Mars's history is sitting under your boots? Mars locked its past into stone. Dried up river deltas, layered sediments, clay-rich zones, all of these are time capsules. When you walk up to a cliff face, you're often looking at stacked layers, each one a different environment. Maybe a calm lake bottom here, a flood deposit there, a volcanic ashfall higher up. You use drills to take cores, rock hammers to break off samples, and portable instruments to scan for mineral types and organic compounds. You photograph everything, note exact locations, orientations and context, then either analyze on site or pack specimens for the lab. Clay minerals are especially important, because many form in the presence of liquid water. If you find clays in certain patterns, you can infer past lakes or groundwater systems. Carbonate layers can hint at different chemistry and possible past atmospheres. Every sample is a trade-off. You can't take unlimited rocks. Storage, mass analysis time, and contamination risk all constrain what you keep. Some high-value cores might be sealed in special tubes and stored for a future sample return mission. Others you grind, heat, or dissolve right on Mars, feeding instruments that search for organics and fine-scale chemistry. Geologists on Earth watch your data in delay. They send suggestions for the next targets, ask for close-up images, request extra cores, but because of the light time lag, a lot of final decisions are yours. You are the hands, eyes, and judgment at the site. When you choose where to drill, you are deciding what kind of Martian story gets told back home. Surface rocks are one thing, but the surface is also where radiation is highest. What happens when you start pushing down into caves, lava tubes, and ice deposits, where the environment changes completely? Radiation drops fast once you get a meter or two below the surface. Caves and lava tubes act like natural bunkers. Orbiter data already points to probable skylights, openings into underground voids, and radar hints at subsurface ice slabs. Those places become prime targets. If you can access clean ice underground, you've found a local source of water and potential propellant feedstock. If that ice has been stable for millions of years, it could also trap ancient material, possibly even biosignatures. EV, as to these sites, are high risk. Terrain is rough, with loose debris, steep slopes, and potential collapses. Rover paths have to be planned carefully, with safe turnaround points. Suits and vehicles need extra dust and abrasion protection. You might lower small robotic scouts into openings before any human gets close. Once you start sampling ice or the edges of caves, contamination control becomes critical. You don't want to bring base microbes into a pristine niche, and you don't want unknown Martian chemistry back contaminating your systems. But if you succeed, these missions can define the legacy of the entire first human stay. Finding thick, accessible ice just a short drive from the base changes your resource map completely. Exploring a lava tube big enough to host future habitats shifts how you think about long-term shelters. Detecting unusual chemistry or structures in protected subsurface zones could be your best shot at preserved evidence of past life. All of this exploration sounds precise and careful on paper. In reality, you are tired, overloaded, and repeating complex procedures hundreds of times. What happens when EVAs start to feel routine, but the planet is still lethal? On the ISS, spacewalks are rare and rehearsed in detail for months. On Mars, EV, as risk becoming normal work, because so much of your job requires going outside. That routine feeling is dangerous. Fatigue and familiarity can push you to cut corners. Maybe you rush a seal check because you've done it 100 times. Maybe you carry an extra tool just this once, and overload a tether. Maybe you walk a bit farther from the rover than the plan allowed, because the rock outcrop is just right there. The environment does not forgive that. A small mistake with a glove seal, a misstep on loose regolith near a slope, a misunderstanding on comms between you and the rover driver, any of these can kick off a problem chain. So the base leans hard on discipline. You refine suit donning procedures again and again, shaving off unnecessary steps but locking in critical ones. You run emergency drills, simulate a torn suit, a lost comms link, a stuck hatch, so that when something weird happens for real, your first moves are automatic. After each EVA, you debrief. Even minor issues get logged. A valve that was harder to turn than usual, a moment of dizziness, a glitch in a sensor. Engineers and safety teams go through those logs later and look for patterns. Is a certain connector degrading faster than expected? Are certain procedures causing repeated near misses? Every new rule and hardware tweak is written in those small failures and surprises. Over months, your EVA techniques get sharper, but the risk never goes to zero. You learn to treat routine as a warning sign. When a task feels too normal, that's exactly when you remind yourself that one bad minute in 0.38 G, in a thin suit surrounded by almost vacuum, can end not just your day, but the whole mission's margin. And all of this exploration is happening from a base that, at the start, is basically a camping setup on a dead world. If you're going to last 1,000 days, you can't stay in camping mode forever. What does it look like when that temporary landing camp has to turn into a real outpost, with buried habitats, printed walls, and a growing web of plumbing and power that either scales up or strangles you in complexity? At the start, your base on Mars is basically a pile of cans on the dirt. Maybe you have a couple of rigid modules that came down before you, an inflatable habitat, and the spent landing vehicle turned into extra living space. All of it is designed, built, and tested on Earth. Layouts were chosen by committees, not by people who have actually lived years in 0.38 G, surrounded by dust. For a while, you just live with it because you have no choice. Very quickly, you find out what actually works and what doesn't. You learn which room arrangements keep noise and light from driving people crazy, which corridors create traffic jams, and which open areas become bottlenecks. You find out which flooring handles constant tracking dust, which fabrics get destroyed fastest by tiny grains, and which coatings actually shrug off abrasion. You watch filters and see how often they clog in real Martian conditions, not in clean test labs. At first, everything feels cramped. Sleeping quarters are small, storage is packed, labs double as dining areas or meeting rooms. You start putting tape marks on floors, temporary shelves on walls, hacking together solutions just to make daily movement tolerable. After a few hundred days, the base interior no longer looks like the perfect render on someone's design slide. It looks like a lived-in machine, with modifications everywhere, because field data has replaced guesses. But you can only do so much rearranging inside thin cans sitting on open ground. Radiation and micrometeoroids don't care that your interior layout is better. How do you actually make the whole base safer, long term? You go down or at least under. The best passive shield you have is regolith, a couple of meters of it piled over your head. That means a big part of base building on Mars is just moving dirt. You use bulldozers and robotic haulers to push regolith onto and around your modules. You build ramps of soil against their sides. You design inflatable tunnels or modular corridors that can be laid in shallow trenches, then covered. The goal is simple: put mass between you and the sky. On day one, the base looks like a small camp, bright modules sitting on bare ground, cables exposed, tanks visible. As the months pass, that changes. Structures get berms around them. Some disappear, almost completely under mounds of dirt, with only airlock doors and small parts of hardware exposed. When new inflatable volumes arrive, you don't just plug them in and leave them exposed. You drop them into prepared trenches and bury them as quickly as power and schedules allow. By the time you approach day 1000, the base has turned into a low, irregular bunker network. From a distance, it looks less like a space station and more like a series of dusty hills with a few hard edges. Inside, radiation levels in key areas are significantly lower. Micrometeoroid risk is drastically reduced. You pay for that with a lot of heavy equipment hours, maintenance on movers, and endless dust battles, but you've traded away some fear of the sky for more confidence in the ground. Physical shielding is one part, but you can't keep shipping steel and concrete from Earth forever. How do you start building real structures mainly out of Mars itself? You start experimenting with Martian concrete. Raw regolith is the base ingredient. One approach is to mix it with binders that came from Earth, like certain polymers or resins, to make a kind of high-tech concrete. Another is sulfur concrete, where molten sulfur, possibly sourced locally, binds the grains. A more advanced method is sintering, using concentrated sunlight or microwaves to heat regolith until grains fuse into a solid mass without any added binder. Robotic or semi-automated 3D printers take these materials and lay down layers to form walls, vaults, radiation shields, storage bunkers, and even test habitats. You print test blocks and torture them. You load them in compression, bend them, heat and cool them over and over to simulate day-night temperature swings. You expose them to dust-laden winds to see how fast surfaces erode. You track cracks, spalling, and any sign that the structure is aging badly. Each printed structure is both useful and experimental. A printed wall around a solar farm cuts dust and acts as a radiation barrier for equipment. A printed shell over an inflatable greenhouse takes some of the load off your imported structural elements. With every successful print that survives a few hundred sols without serious issues, your confidence grows. You start seeing what a future Martian town might actually be made of. Not fantasy glass domes, but thick, dull, locally sourced shells. Walls and rooms are one thing, but a base isn't just shells. It's the web of stuff between them that keeps you alive. How does that web behave in 0.38 G dust and radiation? The skin of the base is obvious. The underskin is cables, pipes, and ducts. Power runs from solar farms and reactors through armoured conduits. Data links tie habitats, labs, vehicles, and antennas together. Water flows in insulated pipes from storage tanks to taps, farms, and life support systems. Oxygen and other gases move through dedicated lines. Air transfers through ventilation ducts, balancing pressure and temperature between modules. On Earth, these systems have decades of code and standards. On Mars, you find out those standards are only a starting point. Seals that last 20 years in 1G and clean air might start drying and cracking faster under radiation and dust. Plastics that passed all tests on Earth might embrittle in the cold and constant low-pressure environment. Connectors that were designed for clean rooms now face abrasive dust, trying to work its way into every gap. So you build, break, and rebuild. You test different materials for flexible couplings, different coatings on pipes, different connector designs. You change how you route lines, maybe burying more of them in regolith for thermal stability and physical protection. You add redundancy, second cables, backup pipes, alternate routes for critical flows. Over 1,000 days, you're not just maintaining infrastructure, You're discovering what building code should mean on a different planet, where gravity, air, and dirt all operate under unfamiliar rules. Every new module, every new tunnel, every new system you add doesn't just change the engineering. It changes how you live with each other. How does expansion turn into a live test of human society, not just hardware? Space was tight at first. People slept in small bunks, shared workspaces, and had almost no real privacy. As you expand, you have choices. Do you use the next volume for more lab capacity? To get more science done? Do you invest in bigger greenhouses to improve food quality and give everyone more fresh produce? Or do you prioritize private cabins, quiet rooms, and recreational spaces to keep people from burning out? On paper, mission planners back on Earth made these choices in advance. In reality, your experience forces adjustments. Maybe you discover that conflict spikes when people don't have sound, isolated sleep areas, so you push private quarters higher on the list. Maybe the mental health impact of seeing a larger, more natural green area with plants and water is so strong that you sacrifice some lab space to build it. Maybe the crew realizes they need a dedicated, neutral meeting room to handle disagreements without dragging the whole base into it. Physical layout becomes a 3D map of what actually matters to a small human society off-world. You see which corridors people avoid, which corners they gather in, which modules are always noisy and which become informal refugees. The base stops being just a machine and starts being a social diagram in metal and regolith. Future planners will look back at your choices, where you put doors, how big you made the kitchen, how close the gym is to people's bunks, and use that data to design the next wave of habitats. Through all of this, you're not just testing technology. You're testing what humans really need when they are cut off from Earth for years and forced to live under constant physical risk. You learn that some things you thought were luxuries, like a bit of extra personal space or a shared quiet area with a view, are actually structural necessities for keeping a crew stable. But there's another layer that builds in parallel with the walls and tunnels. As you pile regolith, print concrete, and stretch cables, something else is changing that you can't see on any blueprint. The minds and culture of the people inside. What happens to a small group of humans when they are locked into a rust-coloured box for 1,000 days, with no real-time contact with Earth, no escape, and a level of shared risk that never fully turns off? On Mars, isolation is not just about distance, it's about cause and effect breaking down. You can't call home and get an answer in the same conversation. You can't trigger an emergency launch and get picked up in a few hours or days. There is no rescue timeline that makes sense on human scales. Antarctic crews and ISS astronauts already show mood swings, tension, and strange social patterns after months, and they have real-time calls and the option of evacuation. You don't. You're on your own is baked into the light time delay and the launch windows. Your brain learns that very fast, then spends the rest of the mission trying to live with it. At first you feel busy, excited, overwhelmed. There's so much to set up that you don't notice the distance. Then the rhythm settles, and the gap to Earth starts to feel heavier. A family message arrives about something important, a birth, an illness, an argument. You react in your head, but your actual reply won't land for many minutes, and by the time they answer back, the moment has moved on. Emergencies on Earth hit you out of sync. By the time you hear about them, the event is already history. That delay chips away at the sense that you share a common now with anyone not on Mars. That constant low-level disconnect shapes how you sleep, how you dream, and how you think about risk. Subconsciously, you know that if something goes very wrong, there is no cavalry. Help is always at least months away. So you and your crewmates become the final line of response for everything. Technical failures, medical issues, social conflicts. That responsibility never fully switches off. Inside that pressure cooker, your crew dynamics are magnified. With maybe 6 to 12 people, every personality trait gets amplified by repetition. On Earth, if someone annoys you, you can change social circles, get space, or drown it in the noise of everyday life. On Mars, the entire planet outside your social circle is lethal. You see the same faces at breakfast, in the lab, in the gym, and at emergency drills for years. Mission planners try to stack the deck. They use personality testing, simulations, and training runs in analog she habitats. They pick people with a proven ability to handle confinement, stress, and boredom. They train everyone in conflict resolution. They balance nationalities, skills, and temperaments. Even so, long risk, long workload, and monotony twist small quirks into bigger issues. One person's tidiness becomes another person's control habit. One person's dark humour becomes someone else's constant negativity. Over 1,000 days, you end up testing a lot of psychological theory. Does diversity in backgrounds help, or does it add friction? Do people bond more over shared danger, or do small irritations dominate? How much private space does each person really need before stress indicators spike? You see which tools help: regular crew debriefings, anonymous feedback channels to Earth psychologists, structured airing out sessions, and which don't. And the answers you find aren't abstract. They're playing out in your own arguments and reconciliations. Time itself becomes a psychological weapon around the mission's midpoint and beyond. Many long-duration crews show a third-quarter effect, where mood and performance drop not at the start and not at the end, but when you are past halfway, yet still far from done. On Mars, that hit can be especially hard. By then, the base, the view, and even the danger feel familiar. The adrenaline is gone. You know the local hills and rocks well enough that EVAs can feel repetitive. But the physics of orbit say you're still stuck here for hundreds of days. Around that third-quarter mark, people can become more irritable, more cynical, or just flat. Mistakes creep in. Work feels meaningless, even though it isn't. Recognizing that pattern ahead of time is critical. You plan schedule changes, short vacation days where you deliberately lower workload, new science projects or construction tasks that break the routine and give a sense of progress. Maybe you rotate roles for a while, give someone a break from high-stress duties, or bring forward a long-planned base upgrade to inject energy. Managing that slump is as important as fixing a failing pump. A demotivated crew in a hostile environment is a direct safety problem. You track it with performance metrics, sleep stats, psychological check-ins, and more simply by listening for how people talk over meals. When jokes disappear and conversations dry up, you treat that as data, not just people being moody. While all of this is happening, something else grows underneath, almost automatically: a new local culture. After enough souls, your crew stops being just international team from Earth and starts being people who live on Mars. You build your own slang, maybe special words for types of dust storms, for small system glitches, or for certain EVA routes. You create rituals, maybe a short ceremony on every landing anniversary, a standard way of welcoming a new crew rotation, or a quiet habit of watching Earth together when it's visible at a decent hour. You also end up with your own calendar of important days. Some are Earth-linked, national holidays or personal dates, but they happen at odd times relative to the Martian sol, so you adapt them. Other days are uniquely Martian. The sol you first saw a global storm from the ground. The sol the first crop fully fed the crew. The sol a major failure almost went bad. You name local features, small hills, rocks and paths, with names that may never show up on official maps. In less than 3 years, you can already see norms and attitudes that don't quite match any Earth culture. The shared experience that binds you is not language or flag. It's the fact that you all live under a thin sky, in 0.38 G, dependent on fragile machinery, cut off from real-time help. That slowly shifts your sense of identity. Us increasingly means the people here, not the people from my country or the people at my agency. You don't stop being from Earth, but you start being from Mars as well, in a practical, day-to-day sense. As you grow into this, you run into ethical questions that nobody has fully answered. Who actually gets to decide what level of risk is acceptable for an EVA, a new construction method, or a test of a prototype reactor? Officially, there are rules set by agencies and companies back on Earth. In practice, you're the one facing the consequences in real time. If mission control says go on a marginally safe plan, can the commander veto it based on local conditions? If the crew wants to try an aggressive solution to fix a failing system, but Earth says wait, how long do you listen when waiting might mean losing the base? Scientific discoveries raise their own problems. Suppose your instruments start showing strong signs of possible past biosignatures, or even present microbial activity, in a subsurface site near the base. Do you avoid that area to prevent contamination, which might protect science but hurt future resource use? Or do you treat it as a core research target that justifies higher risk and more isolation measures? Science, safety, and long-term colonization plans can all point in different directions. Existing laws like space treaties and national regulations technically apply, but enforcement is slow and weak across hundreds of millions of kilometers. If crew members disagree on how to handle a situation that Earth did not anticipate, you are effectively both the governed and the governing body. You create local precedents, written in mission logs and debriefs, that later lawyers and ethicists on Earth will treat as case law. Mars, then, is not just a testing ground for hardware and human biology, it's a live lab for how power, responsibility, group identity, and ethics work when a small group of humans has to stay alive without a safety net. You learn how much autonomy a remote crew really needs, how much oversight actually helps, and where the line is between smart risk and reckless gamble. And through it all, nothing about the outside environment gets softer. The radiation stays high, the dust keeps grinding, the gravity stays low. Inside, you are trying to build a stable culture. Outside, the planet is still a place where a single technical failure can cascade into disaster. Keeping that culture functioning and that hardware running depends on one invisible thing that everything else rides on: power. Without enough energy, life support, farms, rovers, labs, and even your lights go dark. So what does it actually take to feed a growing base with electricity? On a world with weaker sunlight, brutal dust storms, and no global grid to lean on. Where every watt has to be caught, stored, and defended. On Mars, power is the silent dictator. The sun is weaker here. Mars orbits at roughly 1.5 times Earth's distance, so the sunlight is only about 43% as strong. At the top of the atmosphere, you get around 590 watts per square metre, and less at the surface after scattering and angle losses. A solar panel that might deliver a certain number of kilowatts on Earth gives you well under half of that on Mars, even when it's brand new and clean. That shortfall hits every part of your life. Life support needs constant electricity for pumps, fans, heaters, compressors, and control computers. Heating is a huge load by itself because the air outside is thin and cold, and the planet radiates heat away fast. Communications gear has to push signals across tens or hundreds of millions of kilometers. Rovers and drills need power to move and work. Labs need steady supply for instruments, freezers, and analysis hardware. You can't just plug in one more device because it's useful. Everything goes into a power budget that looks like a brutal spreadsheet, not a wish list. You track watts the way people on Earth track money in a crisis. How much do we generate this sol? How much do we lose to inefficiency? How much do we absolutely have to spend on life support and heating? What's left for science, construction, and comfort? When you add a new system, you ask not just what does it do, but what does it cost in watts and when does it draw them? The thin sun forces you to think of energy as a hard, daily ration. Solar is still your obvious first source. So how do those panels actually perform once you put them down on that dusty ground? Early in the mission, you roll out arrays of solar panels across the regolith on fixed frames or modest trackers that tilt them toward the sun. At first, the numbers look good. Clear sky, low dust, decent angles. Your panels deliver roughly what the model said they would, adjusted for Mars' weaker light. It feels like one thing that finally behaves. Then the dust starts to build up. Not a dramatic storm at first, just normal days. Fine particles settle out of the air and stick to the glass. Output drops a few percent, then a few more. After a few weeks, some parts of the array are noticeably darker than others. If you ignore it, power falls far enough that you start sacrificing non-critical loads. You can't sit around hoping for cleaning events like the ones that extended the Opportunity rover's life, where wind gusts happen to blow panels clear. You design active cleaning from the start. Simple methods include mechanical brushes on rails that move across panel rows, pushing dust off. You might use soft rollers or wipers that don't scratch the surface. More advanced systems use electrostatic shaking, applying high-voltage pulses that repel dust particles and make them jump off the surface. Some missions add small robots, slow-moving panel cleaners that crawl the array like land-based Roombas, powered either by the panels themselves or by swappable batteries. You schedule cleaning runs when power demand is low to avoid adding big spikes on top of your normal loads. Every time a cleaning system passes, you see output bounce back a little on the graphs, sometimes enough to keep greenhouse lights at full intensity or keep a bank of heaters from cycling too hard. You quickly learn that designing for ease of cleaning is just as important as designing for sunlight capture. Flat, continuous surfaces beat intricate, dusty crevices. Access paths, anchor points for tools, and margin for robots all matter. Solar farms on Mars are not set and forget. They are constant maintenance jobs that decide how much slack your whole operation has. Solar alone, however, is at the mercy of night, seasons, and storms. You cannot let your life support be a hostage to the weather. What's the backbone that carries you through the dark and the dust? That backbone is nuclear. A realistic Mars base almost certainly brings compact fission reactors, kilowatt-scale units designed to run for years with minimal intervention. They don't care if it's night or day, summer or winter, clear or stormy. They just sit there and convert nuclear energy into heat and electricity at a steady rate. You wire these reactors into the base as your baseload source. Life support, critical computing, communication systems, and some heating ride on that constant output. Solar and maybe small wind systems then stack on top, handling variable loads, charging storage, and powering high-demand tasks when conditions are good. Nuclear gives you a floor you try never to fall below. The waste heat from the reactors is not just a problem to get rid of. In a cold environment, it's a resource. You can route heat exchangers through habitats and greenhouses, pre-warming air or water before it goes into those systems. That reduces the load on separate heaters. You may run radiator loops through parts of the base that need constant warmth, turning what would have been thrown away as waste into a stabilizing buffer. Having nuclear units on site is also an admission of reality. Mars is too harsh and too unpredictable to trust a single energy source. Redundancy here is not academic, it is survival. You plan for the possibility of a solar array fault right before a storm or a temporary reactor issue at the same time as a bad dust season. The whole architecture is built with the idea that some pieces will fail and other pieces must be there to catch the drop. None of that matters if you can't move energy in time, from when it's available to when you need it. Without a global grid, how do you actually store and juggle power on this planet? On Earth, if a wind farm drops or a solar plant gets clouded, the wider grid can often smooth it out. On Mars, your grid is just your base. There is no external buffer, so you lean heavily on storage and smart scheduling. Large battery banks are the first layer, lithium-ion or more advanced chemistries, designed to operate in partial gravity and low temperatures. They charge during sunny periods when your production exceeds immediate demand, and discharge at night and during storms to keep core loads running. You might add flywheels, heavy spinning masses in vacuum chambers, that store energy mechanically and can respond very quickly to sudden load changes. For longer-term storage, especially to bridge multi-day events, you can use chemical methods, like making hydrogen or methane from water and CO2 when you have surplus power. Then running that fuel through fuel cells or small burners connected to generators when you're short. Energy management becomes part of almost every conversation about base operations. Planning an EVA with multiple rovers far from base. You check how much battery capacity you'll need, how many fast charge cycles that implies, and whether the reactors plus current solar can handle it. Thinking about adding new lab equipment, you look at its draw, its duty cycle, and how it lines up with other loads. Scheduling a big regolith moving project for radiation shielding? You might push it into a season with stronger sunlight, so the extra motor power doesn't cut into life support margins. Over 1,000 days, your base effectively becomes a classroom in advanced off-grid living. You learn how much redundancy is enough, what failure modes you didn't predict, and how human behavior interacts with energy constraints. You also discover that people adapt faster than you expect. Habits form, turn off lights when you leave a room, batch high-power lab runs when the sun is high, delay non-critical tasks when storage is low. Everyone becomes, in some sense, an energy manager. Underneath all of this, one fact is clear. Power is not optional. Without it, you can't run air, water, farming, EVAs, or communication. It's the base layer under every other layer of survival and exploration. And power is exactly what you need if you want to tackle one of the biggest reasons you came here at all, the question that has hung over Mars for decades. With thin air, weak sun, and a fragile energy budget, you still spend precious watts drilling, heating, and analysing rocks and ice. Why? Because buried in that stone and frozen water might be the first hard evidence that life ever existed somewhere other than Earth. So what does your first 1,000 days look like when you focus not just on staying alive, but on hunting for signs of alien life under your boots, in soil that might hide organics, and in ice that has been sealed off for millions of years? You didn't come to Mars just to fix pumps and sweep dust. The big prize is the life question. From orbit, probes have already mapped clay minerals, hydrated salts, and shapes that look like ancient shorelines and river deltas. Rovers like Curiosity and Perseverance have drilled rocks, found organic molecules, and confirmed that some past environments were habitable by Earth standards. But habitable is not the same as inhabited. No one has seen direct evidence of Martian life. You're the first person who can close that gap with your own hands. When orbiter data and old rover results say, this basin was once a lake, you can actually go there. You can stand at the foot of an ancient delta, point and say, we drill right there. You can adjust on the fly if the rock is softer or harder than expected, if layers tilt differently than the maps showed, or if you spot an unexpected outcrop that doesn't fit the models. The search for life is no longer a slow, remote control puzzle. It's your normal workday. Sample runs, lab time, data review, repeat. That sounds simple until you hit the chemistry. Martian soil is not a clean canvas. It fights your instruments. How do you tell a true biological signal from tricks of weird chemistry? One big headache is perchlorates, reactive chlorine-oxygen compounds that are present in many Martian soils. When you heat samples in some types of instruments, perchlorates can break down and destroy organic molecules, or create confusing breakdown products. That can make you think, no organics here, when in fact, you just burned them up in the analysis step. Past missions had to redesign and reinterpret their experiments because of this. In your lab on Mars, you have more options. You use wet chemistry kits that dissolve samples at controlled temperatures, avoiding the worst of perchlorate breakdown. Microfluidic devices route tiny amounts of liquid through channels with sensors that can pick up specific organic molecules, amino acids, lipids, or other complex compounds. Microscopes let you look directly at fine structures in rocks and ice. More advanced gear might include small instruments that can test chirality, whether certain molecules prefer left-handed or right-handed forms, which is a strong biosignature on Earth, or even miniature sequencers or other molecular analyzers. Every time you see something interesting, an unusual organic profile, a structure in a rock slice that looks a bit like a cell, a gas pattern that hints at metabolism, you have to attack it from every angle. Could pure chemistry, with no biology, produce this pattern? Could your own contamination be faking it? Is there a simpler, non-biological explanation? You live for 1,000 days on that edge between "we've found life" and "this is just strange geology and chemistry we don't fully understand yet." Surface material only tells part of the story, and radiation has been chewing on it for millions of years. So where do you look if you want the best shot at preserved signals? You go down. High-energy particles from space break complex molecules on the surface over long timescales, but their reach is limited. A few meters of rock or ice can shield organics pretty well. So one of your most important tools is the drill. You push bit after bit into the ground. 1 meter, 2 meters, in some places maybe 5 or more, depending on your hardware and geology. The cores that come up are not just dirt, they are vertical timelines. In old lakebeds, you see fine laminations, thin layers that might represent seasonal deposits or changing water chemistry. In possible hydrothermal areas, you find altered rocks that interacted with hot water, which on Earth are often associated with microbial life. In former brine zones, salts and minerals might have trapped organic molecules and microstructures like a freezer. In the lab, you slice these cores carefully. Some pieces go to microscopes, some to instruments that sniff out organics and measure isotopes, ratios of different forms of elements like carbon and sulfur. Biological processes often skew those ratios in recognizable ways. If Mars ever had microbes that ate, breathed and left waste, tiny chemical traces of that metabolism might still be locked in these protected cores. You're drilling for those signatures, and every meter you go deeper is a bet that you're getting closer to untouched history. All the while, there's a problem you can't ignore. You're shedding your own biology into the very world you're trying to study. How do you keep from ruining the experiment? No matter how clean your procedures are, you are a walking cloud of Earth life. Bacteria on your skin, microbes in your breath, spores on your equipment, all want to ride along. Planetary protection rules try to keep that under control. Before flight, critical hardware is sterilized. On Mars, you set up clean zones with stricter protocols for handling the most sensitive samples. You use dedicated tools for high-value sites with extra cleaning steps between uses. You limit how close certain EVAs can get to especially promising locations before they've been properly sampled robotically. All of that slows you down. It adds steps, delays, and extra complexity to missions that are already hard. But if you ignore it, you risk seeding Martian sites with Earth microbes that could survive in protected niches, then confuse or destroy future life detection experiments. The paradox is ugly. The longer humans live and move around on Mars, the more Earth life we inevitably leak into the environment, and the harder it gets to be sure any future signal is truly native. That's why your first 1,000 days are so critical. This is probably the cleanest human window we will ever get on Mars. Every decision you make about where to go, how to sample, and how strictly to enforce cleanliness affects not just your own science, but the integrity of all future searches. And then there's the possibility that the long, painful care pays off. What happens to you, and to everything, if a signal finally comes back that passes every test? Picture a core sample from a sheltered clay layer, deep below the surface. In the lab, instruments pick up complex organic molecules arranged in patterns that don't match any known non-biological process. Isotope ratios line up with what you'd expect from metabolism, not random chemistry. Under a microscope, you see repeating microstructures, cell-sized, with shapes and internal textures that look like something that once grew and divided. You rerun the tests, you check controls, you run contamination checks. The signal holds. Even before Earth scientists, working off your transmitted data, formally confirm it, your world tilts. You are no longer living on a dead rock. You are sharing a planet that at some point hosted life. Maybe it's extinct and only fossils remain. Maybe some microbial pockets are still active in deep brines or warm spots. Either way, Mars's lifeless is gone. From that moment, every plan changes. Mining, drilling, large-scale construction, and especially any talk of terraforming, all have to be weighed against the existence of a second biosphere, even if it's just microbes. Do humans have the right to overwhelm it? Are you allowed to intentionally alter an entire world that has its own biological history? How do you balance the drive to expand with the responsibility not to erase the only other example of life we've ever found? For you personally, the base stops feeling like an outpost on a blank canvas. It feels like a station on the edge of something alive, or once alive. You're no longer just explorers and settlers. You're neighbours or intruders, depending on how you look at it. And while you're wrestling with that, Mars keeps pushing back in more direct ways. Systems still fail, the environment still punishes mistakes. Life, whether alien or not, doesn't change the fact that you are held up by machines that can break. So after 1,000 days of searching for microbes, you're still facing a more immediate question. Not, does Mars have life? But, how exactly does Mars kill you when things go wrong? And what failure chains are you constantly trying to break before they reach the point of no return? On Mars, the cleanest, fastest way to die is simple: lose pressure. Outside, the atmosphere is around 600 pascals, basically a thin CO2 fog. Inside your suit or habitat, you sit at tens of thousands of pascals. That pressure difference is always trying to push air out through any weakness. A punctured suit from a sharp rock, a micrometeoroid punching a pinhole in a wall, a bad weld that finally lets go after hundreds of thermal cycles. Any of those can turn a safe volume into vacuum in seconds. If a suit tears badly, you have less than a minute of useful consciousness, probably much less before your blood oxygen crashes. Your lungs can't pull enough gas from nearly empty air, water in your eyes and mouth starts to boil away, and you black out. In a habitat, a serious breach can drop pressure fast enough that you don't have time for a casual response. That's why your entire EVA and habitat design is built around making sure no single failure takes you straight from fine to dead. You use redundant seals on airlocks. You design suit joints so a single damaged ring doesn't fully open a path to vacuum. You divide the base into compartments with bulkheads and doors that can be slammed shut to isolate a leak. Sensors constantly watch pressure and leak rate, not just total pressure, but how fast it's changing. A tiny, slow leak might be acceptable for a while, as long as you can top up from reserves and schedule a repair. A sudden change triggers alarms and automatic actions. You drill for that, drop what you're doing, seal hatches, check for missing crew, and move to safer zones. You live with the knowledge that the air around you is always trying to get out. Even if you keep the air in, you still have to worry about what that air can do to you when it catches fire. How does a flame behave when your whole world is a pressurized tin can? In a Mars habitat, you often run a higher oxygen fraction and a lower total pressure than Earth's sea level. That's good for structures because it reduces stress on walls and windows, but it changes fire behavior. Depending on the exact mix, flames can ignite more easily and burn hotter, or spread differently than you'd expect. Smoke has nowhere to escape except into your lungs and filters. You can't just open a window. The Apollo 1 fire and serious incidents on Mir and ISS showed how fast things can go bad in sealed habitats even close to Earth. On Mars, you add distance, cold, and dust contamination to that list. You treat every spark as a potential chain reaction. Cables are shielded and routed to minimize rubbing or chafing. Connectors are locked and strain relieved. Materials inside the habitat are chosen for low flammability and low toxic smoke when they do burn. You use metal where you can, flame retardant fabrics where you can't. Heaters and high-power equipment have extra temperature sensors and shutoffs. Fire drills are not optional. You rehearse what happens if a smoke detector trips in a lab, in the greenhouse, in an airlock, at night. You practice grabbing masks, extinguishers, and thermal cameras and moving in teams. Some habitats are designed with rapid atmosphere dump systems for certain compartments, ways to quickly lower pressure and starve a fire of oxygen in a controlled way, then repressurize later. Using that is a last resort, but it's better than losing the entire base. Fire is not just another risk item. In a sealed can, it can turn your environment hostile faster than almost anything else. Then there are the things that don't flame up, but still quietly poison you. How do you deal with toxic leaks when outside is even worse than inside? Your base uses chemicals that are not friendly. Ammonia in coolant loops, hydrazine, or other propellants stored in tanks from older landers or used in situ propellant production. Industrial gases in ISRU plants that turn CO2 and water into fuels and oxygen. All of these are around you. Some have strong odours. Others are almost impossible to detect by smell. Some act fast on the nervous system or lungs, knocking you down before you know what hit you. On Earth, if a tank leaks in a building, you can often evacuate and let responders in with heavy gear. On Mars, there is no better air outside. If a toxic cloud forms in a module, you either contain it, filter it and treat it, or you risk spreading it through shared ventilation. That's why sensor networks track not only O2 and CO2, but also specific, dangerous gases at low concentrations. Alerts may trigger automatic valve closures, fan shutdowns or reroutes, and forced isolation of certain ducts. You train with respirators and emergency masks staged throughout the base. Compartmentalization becomes critical, not just for pressure loss, but for contamination control. You design work cells so that a leak in one system doesn't automatically dump fumes into sleeping quarters or key control rooms. In emergency response drills, you practice entering a contaminated zone in protective gear, shutting off valves, and then retreating, all while watching your own exposure time. These individual events are bad enough, but Mars often hits you with cascades. What happens when one failure drags multiple systems down at once? Systemic failure is where the environment shows its real teeth. Take a dust storm, for example. Heavy dust cuts your solar inputs. With less solar power, you rely more on batteries and reactors. If a reactor is down for maintenance or underperforming at the same time, you might have to shed load, cutting heating in less critical zones. Lower heating means some external lines and modules cool more than usual. Metals contract, seals stiffen, and fluids can thicken or freeze. Batteries don't like extreme cold. Their output and lifetime drop. Now imagine that in the middle of this, your main antenna develops a fault, maybe from thermal cycling or dust abrasion. Communication with Earth becomes patchy or fails. Your ability to get troubleshooting help or confirm next steps drops right when you need it. You're now juggling low power, marginal temperatures, and reduced outside support, all at once. Mars doesn't throw each problem at you in a neat, isolated way. Its baseline conditions, cold, thin air, dust, radiation, delay, mean that when one thing fails, it often stresses others. Your operating procedures, checklists, and simulations focus on cutting these chains. If power drops, what do you shut down first to preserve life support? If heating falters, which lines do you purge or insulate first to prevent freezing? If comms weaken, what local authority does the crew have to make bigger decisions without waiting? You plan cross-training so that crew can cover multiple roles if someone gets sick or overloaded. You design systems so that a local failure doesn't instantly spread through shared loops. Over 1,000 days, you will see small chains start, and sometimes you'll only barely stop them before they tip into something worse. Living through close calls changes how you think about all this. You stop seeing Mars as generally dangerous and start seeing specific odds and trade-offs. How does your idea of the acceptable risk shift after years in this environment? At the beginning, you think in absolutes, we will make this safe. We will design around every failure mode. After 1,000 days, that language feels naive. You've seen pumps fail early, valves stick, sensors give bad readings, and software throw glitches. You've watched teammates stumble from fatigue, and you've maybe seen an EVA get closer to disaster than anyone likes to admit. If the mission is long enough, you might even lose someone to an accident that looked impossible on paper. That experience doesn't make you reckless. It makes you precise. You stop chasing zero risk because you understand that's not possible here. Instead, you learn to ask, what risk level are we actually living with right now? And is that worth what we gain? You accept some dangers because they buy you critical knowledge or infrastructure, like pushing a rover longer to reach a major ice deposit. You refuse others because they are just ego or impatience dressed up as courage. To people on Earth, your new normal would look extreme. They live in a world where emergency services are minutes away, where gravity, air, and temperature sit in narrow, comfortable bands most of the time. For you, walking into a 0.38 G environment with tens of kilopascals of pressure in your suit and 600 pascals outside feels routine. You strap into rockets, crawl under reactors, and run drills for leaks and fires as part of your week. That mindset, accepting a constant elevated level of danger as the price of doing meaningful work, becomes standard for you and your crewmates. It's not bravado, it's adaptation. You weigh every plan between worth the risk and not worth losing someone over, and you understand that line better than anyone who has never left Earth. And yet, even while you juggle these risks, the mission is not just about surviving and studying, it's also a beachhead. People back home are already asking, when do we scale this up? When does an outpost become a settlement? And when do we move from visiting Mars to truly living there? So after 1,000 days of close calls, small victories, and constant hazard, what does it look like when you try to grow this fragile foothold into something bigger? More people, more infrastructure, maybe even talk of children and terraforming. On a planet that has made it very clear, it doesn't care if you stay. If every drop of fuel has to come from Earth, Mars never grows past a stunt. That's why somewhere in your first 1,000 days, you end up babysitting chemistry plants that feel more like refineries than science experiments. The core idea is simple. Use what Mars gives you. The air is mostly CO2. The ground in many places hides water ice. Sabatier reactors take CO2 and hydrogen and turn them into methane and water. Electrolyzers take that water and split it into hydrogen and oxygen. Methane and oxygen together make rocket propellant. In practice, these are not neat little lab rigs. They're industrial systems with compressors, reactors at high temperature, heat exchangers, catalysts that can foul, valves that can stick, and tanks that can leak. You feed CO2 from the outside atmosphere into compressors, purify it, and push it into Sabatier units. You bring in hydrogen that was launched from Earth or eventually recovered from local water, and you run the reaction endlessly, tracking flow rates, temperatures, and conversion efficiency. Downstream, you cool the output, separate methane and water, send water to electrolysis, and loop hydrogen back. Your job is to keep that whole chain stable. These plants run for months, aiming to fill huge storage tanks with liquid methane and liquid oxygen. If they work as designed, rockets can land on Mars mostly empty, refuel from local products, and depart. That slashes launch mass from Earth. If they don't work reliably, every future crew depends on tanker flights from Earth delivering pre-made propellant, which kills flexibility and ramps up risk. When you're tightening a bolt on a Sabatier line or swapping a sensor on an electrolyzer, you're not just doing routine maintenance. You're deciding whether Mars will ever have regular traffic or always be a one-off destination. While those plants grind away, people back home are projecting growth curves. You and your crewmates are the first wave, maybe half a dozen to a dozen people. The plan is that later missions won't start from scratch. They'll dock new habitats onto your existing tunnels, connect new greenhouses to your life support, and tie fresh reactors and solar fields into your grid. 10 people become 20, then 50, maybe more, spread across linked modules, each arrival bringing skills and mass, but also new failure paths. Your 1,000-day window gives planners real numbers for the first time. How fast do seals actually degrade? How much labour does it take per person to keep life support, power and farms running? Does adding more people make the base more resilient? Because there are more hands and more redundancy, or more fragile? Because one system failure now affects more lives and more complex networks. You see that firsthand. Each new module is one more thing to heat, pressurize, clean, and maintain. Each new reactor or solar field adds power but also parts that can fail. Each extra human adds capability, but also food demand, water demand, and psychological load on the social system. You learn where the growth curve bends from more is safer to more is balancing on a knife edge. Somewhere in this expansion, one topic always comes up in private conversations, even if the official documents barely touch it. Children. Not now, not tomorrow, but eventually. If Mars is ever going to be more than a research outpost, someone will ask whether it's possible or ethical to bring pregnancy and childhood into 0.38 grams under higher radiation. Biologically, we have almost no answers. Will a human embryo develop normally in partial gravity? Does reduced mechanical load on bones and muscles during growth cause permanent structural problems? How much does chronic radiation during gestation and childhood raise the risk of defects or diseases? Psychologically, what does it mean to be born in a metal cave, under a sky you can't breathe with no memory of Earth? Legally and ethically, it's just as murky. What laws apply to a child born millions of kilometres from any nation's soil? Who has jurisdiction if different agencies or companies disagree on rules for education or medical decisions? In your first 1,000 days, you won't raise a generation, but you will generate the medical data and lived experience that rule this discussion. How your bones respond in 0.38 G, how your cardiovascular system adapts, how your radiation exposure accumulates. All of that feeds into models about whether anyone should even try to have a child on Mars. Then there's the biggest long-term fantasy of all, changing Mars itself. Talk inside a base long enough, and someone will bring up terraforming, thickening the atmosphere, warming the surface, maybe even making liquid water stable again. It sounds tempting, turn this lethal world into something more like a harsh version of Earth, but the physics is a lot less friendly than the concept art. Once you're here, you see just how cold, thin, and dry Mars really is, day after day. You know exactly how much energy it takes just to keep a small base warm and pressurized. Calculations show that the easily accessible CO2 reservoirs, polar caps, adsorbed in regolith, probably aren't enough to build a thick, warm atmosphere like Earth's, even if you could release them all. Any real climate change project would take centuries or longer, demand huge industrial machines, and still run into unknown feedbacks. Your 1,000 days kill off the quick terraforming dream. Mars stops looking like a fixer-upper and starts looking like what it is, a full planet with its own deep history and slow climate machinery that doesn't bend easily to human schedules. You may still talk about long-range interventions, darkening ice to increase absorption, releasing greenhouse gases, bulk importing volatiles from elsewhere, but now you frame them in honest terms, multi-generational, risky, and possibly never reaching an Earth-like endpoint. Settling Mars is not about flipping a switch to make it habitable. It's about building and maintaining bubbles of habitability inside a hostile overall environment for a very long time. As more missions arrive and bases expand, the question of who gets to decide anything here stops being theoretical. At first, your mission operates on pre-signed agreements, rules of behavior, safety protocols, and chains of command laid out by agencies or companies. Everyone knows who the commander is, who can override whom, and what the official risk limits are. But as infrastructure grows and more organizations put hardware and people on the ground, those neat lines blur. Who owns the mineral resources under your main habitat, if one module came from a government program and another from a private company? Who gets first rights to a major ice deposit within rover range? If different groups both want it? If crews from two different nations disagree about how to handle a beamed power installation? Or how to route a shared road? Who arbitrates? On Earth, you could go to courts or international bodies. On Mars, delays and limited enforcement make that slow and weak. In practice, your mission logs, conflict resolutions, and joint agreements become proto-laws. When you handle a dispute over shared equipment, and the solution holds, that goes into the record as a precedent. When base commanders from different organizations sit down and sign a local resource sharing agreement, that document becomes the seed of Martian property norms. Over time, patterns set in your first 1,000 days, how you handle accidents, how you assign blame, how you adapt Earth rules to Mars realities, will be used by future generations as, this is how it's done up here. You're not trained legislators, but you are, by necessity, writing the first rough constitution of off-world society through daily choices made under pressure, not in ideal conditions. Governance stops being an academic question and becomes part of operations. All of this, propellant plants, growing population, arguments over kids and terraforming and resource rights, is happening while you personally are changing. Mars has spent 1,000 days rewriting your body and your mind, pushing you away from the version of you that left Earth. As you approach that 1,000-day mark, you face a new kind of question, not just, can humans live here? But what have these 1,000 days already turned you into? And are you still the same kind of human who left Earth? Or something slightly different that now belongs more to Mars than to your original home? By day 1,000, Mars has literally rebuilt your body. Years in 0.3, 8G, steady radiation, recycled air and water, artificial light, closed diets, all of that has pushed your biology into a shape it never saw on Earth. Bone density scans show changes in your hips, spine, and legs, even with constant exercise. Some areas may have stabilized at a lower level than Earth normal. Muscle structure has shifted, favoring the loads you actually experience here. Less vertical pounding, more careful, controlled movement in a lighter field. Your immune system has been living in a hyper-clean, low-pathogen environment, but under constant radiation stress. Blood tests show altered white cell counts, change in inflammatory markers, maybe new baselines for how your body responds to minor infections. Gene expression profiles, if you compare them to your Earth-side samples, show differences in pathways linked to DNA repair, stress response, and metabolism. Mars has been quietly telling your cells, adapt to this. And they listened. If you decide to go back to Earth, your body has to climb a gravity wall it hasn't seen in years. At 1G, your heart has to push blood harder, uphill. Your bones and joints suddenly feel every kilogram of mass again. Your spine, which stretched a bit in low load, gets compressed. Rehab isn't a week of light workouts, it's months of guided reconditioning. And even then, some things may not fully return to your pre-Mars state. Every extra year you spend up here tilts the curve farther. At some point, going back becomes less a trip home and more a major medical project. Practically, the longer you stay, the more your body belongs to Mars. Your mind has changed just as deeply, but in a different way. By now, orbital windows and light time delays feel normal. You think in synodic periods, those roughly 2-year gaps between good launch opportunities. A message that takes 15 minutes one way feels fast. If the delay creeps toward 20 minutes, you register it. The way people on Earth notice a lag on a bad video call. You schedule your day around when Earth is awake, when satellites pass overhead, when power peaks and when dust storms usually rise. Distances have been stretched too. Crossing a continent in a few hours on a plane now sounds almost ridiculous to you. You've lived with distances where a simple hardware resupply can take months, and a decision about whether to launch a mission can lock things in for years. When you say local, you might mean within 50 kilometers of the base, or within light minutes in radio terms. 2 worlds, rotating and orbiting, are both inside your mental neighborhood. You've also internalized the idea that causality has a delay. You send a question, the answer comes long after you've already moved on. You run an experiment, the full interpretation might arrive from Earth teams weeks later. You no longer expect the immediate feedback loop that Earth life trains into people. That changes how you reason. You plan with more buffer. You think further ahead. And you tolerate uncertainty in a way that would feel strange to your earlier self. Stepping back, your presence here has cracked a basic assumption of human history. For as long as there were humans, we live on Earth was more than just a fact. It was the definition of the species. After 1,000 days on Mars, that sentence no longer covers reality. Here you are, a small bubble of human civilization, running mostly on local resources, linked to Earth by data and occasional cargo, but functioning day to day without any physical connection. It's a fragile bubble, yes, but it works. That alone rewires thinking back home. Risks that once looked like absolute human extinction now look more like catastrophe on one planet. Still awful, but not the end of everything. Conversations about long-term survival, species-scale projects, and what destiny even means now have to include the fact that humans can actually move some piece of their world off-planet and keep it going. You have turned multi-planet species from a slogan into a data point. As your planned mission window closes, you face a decision nobody in history has had before. Do you go back down the gravity well and thick air that built you, or do you stay on the thin, harsh world that has been rewriting your body and mind? Some choices are simple. If your health data says your bones or cardiovascular system are in trouble, or you've accumulated more radiation than is safe for another 1,000 souls, going back might not be optional. Family, promises, and career paths back on Earth pull many people home. Agencies and companies also need veterans back in control rooms and design teams. But not everyone feels that pull the same way. Some crew members will push hard for the chance to stay, to roll straight into the next mission, to become the first truly long-term Martians, maybe even to commit most of the rest of their working life to this planet. They know the physical costs, they understand the risks. For them, the idea of trading this frontier, with all its danger and meaning, for a desk on Earth feels wrong. The fact that staying is even on the table is the breakthrough. Home is no longer automatically the planet of your birth. It's now a choice shaped by biology, logistics, loyalty, and identity. Some humans will live and die on a world they were not born on, and that will stop being shocking as more waves of crews cycle through. When you look back at what your first 1,000 days actually did, the numbers are huge. Terabytes of geological data, mapping ancient lakes, rivers, and lava flows. Continuous radiation logs that finally pin down what long-term surface exposure really means. Medical scans and blood work that show how 0.38 grams dust and isolation reshape a human body. Engineering records full of failures, patches, redesigns, and workarounds. The real manual for how to keep metal and plastic alive on Mars. But the deeper impact isn't in those spreadsheets and archives. You've answered a more fundamental question. Can a creature shaped by Earth's gravity, air, and day-night cycle build a stable life in a place that has none of those things? Not just for a week or a month, but for years, under constant stress without going insane or falling apart physically. Your presence here, your daily routine of checks, EVAs, farm shifts, drills, and debriefs, is the proof. You took an environment that should kill you in minutes and wrapped it in layers of physics, chemistry, biology, and culture until it became survivable. In doing that, you've expanded the practical meaning of habitable in the universe. It's no longer just about planets that happen to look like Earth. It's about any place where a clever, stubborn species can build its own conditions and hold them long enough to matter. Your 1,000 days on Mars aren't the end of the story. They're the point where human history splits, one branch staying on the planet that built us, another learning, often the hard way, how to live somewhere that absolutely did not. From now on, when we talk about where life can exist, we have to include not just natural oases, but the hard-won outposts we build for ourselves on worlds that were never meant for us until we arrived. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.